We are going to go to the next talk of this session by Professor Sanyasiraju of IIT Madras, and I request Professor Subir Das to chair this session.
Hello. Hello, sir. Uh, sir, please unmute, sir. Uh-huh.
Sorry, very sorry.
Yes.
Hello. Good afternoon to
Good
Professor
afternoon.
Som and also to Professor Das and all others.
Okay. Sir, Professor, it is my immense pleasure to introduce Professor Sanyasiraju. He is a professor of the Department of Mathematics at IIT Madras. Before joining to IIT Madras, he worked in NAL Bangalore and IIT Guwahati before moving to IIT Madras in December 1998. His area of research is computational fluid dynamics. He's a very renowned person in CFD. And he's a very good teacher. What I have heard from my colleagues, junior colleagues,
I don't know.
He's a very great teacher. And not only that, he's an active researcher. Today, I was going through his CV and I have seen his recent publications: Applied Mathematics and Computation, International Journal of Heat and Mass Transfer, International Journal of Numerical Methods for Fluid, Communication in Computation and Physics. So you see, these are all very renowned journals. And another thing I know that everybody knows Professor Sanyasiraju is a great academician. He's also a great administrator because he was the chairman of GATE for 2 years. I also worked under him. So now I hand over the mic to Professor Sanyasiraju.
Thank you, Professor Das. I mean, very, very kind words. I mean, much more than what I deserve. Thank you very much for that. I hope my voice is clear. Can somebody?
Yes, sir. Yes, sir. Yes, sir.
Yeah. Thank you. Okay, straight away. So how much time I have? So right now it is 12:15.
Yeah, you can take, sir, up to 45 minutes, I think.
Okay. Half an hour. That means
half an hour, sir.
Maybe 12:40 like that. I'll try.
Yeah.
Okay. So that I don't want to eat up the participants' lunchtime. So I'll try my best. Okay. So I'll go to the sharing my screen. Yeah, I'll go with the entire screen. I hope the slide is visible. It's taking time.
Yes, sir. Yes, sir. It
is visible, right? Yeah. Okay. Okay. So good afternoon, everyone. So I'll be talking something on some upwind options for the meshless RBF schemes with PDE points. Of course, quite a few words in this title are not directly understandable, but during the course of my lecture, I hope I can make every word of this is understandable. Okay, so please some patience. Okay, this is the outline. But anyway, during the course, you can see what are the things I'll be dealing with. So generating a suitable grid is one of the major difficulty in numerically solving fluid dynamics problems, particularly. Of course, even otherwise, this grid is very important because numerical solutions of many of the conventional numerical schemes depends on how good is this grid. And similarly, solving the convection dominant problems using standard numerical schemes is also challenging due to the spurious oscillations generally appear in the solution. This is the nature of the this particular type of equations. So therefore, a mesh-free numerical integration scheme which can solve complex problems, particularly these convection dominant ones, accurately is a very desirable desirable work, maybe we can say. And radial basis function based mesh-free schemes are powerful and easier to implement. Okay, again, I'm using another radial basis function. What exactly is that? I'll make it clear in a few slides. So a function from RD to R is called radial, provided there exists a univariate function. Okay, so this dimension can be anything. This D can be anything, any number, doesn't matter. However, there should be a univariate function phi, something like this, 0 to infinity to R, satisfying this condition where this R is nothing but the Euclidean distance in R. So because we are dealing with the univariate function which is based on the Euclidean distance, therefore this particular method which is based on these radial basis functions is independent of the dimension of the problem. This is a great importance in application problems. So that's the reason why we use these particular functions to solving certain fluid dynamics problems. Okay, so it provides solutions over scattered data. This is important. Okay, of any dimension without local connectivity. You see, this is the word is important. Without local connectivity. What is this gridless or meshless compared to the conventional schemes is that connectivity of the points is not important. That doesn't mean that there are no points. I mean, if there are no points, I cannot compute any numerical solution. Any numerical solution, one has to choose certain discrete points in the domain and we compute the solution over those discrete points. However, in the grid-based methods, the connectivity of those points is important and that becomes irrelevant as far as this meshless methods is concerned. So that's the difference between these two. Okay, and here it depends only on the Euclidean distance between the points and also allows the reconstruction of partial derivatives throughout the domain. And there are two types of infinite RBFs, which are infinitely or smoothwise piecewise smooth functions. Okay, and one simple example is the simple distance function. You just simply take the distance function in even in 1D, so that can be treated as a radial function. And some of the examples here are multi-quadric, inverse multi-quadric, Gaussian, polyharmonic splines, etc. These are some of the functions which can be considered as radial functions. And please note that as far as the radial basis is concerned, it is the translates of the basis function. So that means you identify certain points in your domain and consider the translates of the basic function, and that gives you the basis radial RBF. Okay, and one of the important radial basis function is the multi-quadric. Okay, defined. You can see there are two equations I gave you here. In either one you can use. I mean, you can also see there is a parameter involved in this, either epsilon or c. Okay, so this is what is called the multi-quadric radial basis function, and I mean you can also see how that function looks like for particular value of c or epsilon, doesn't matter. Both definitions are available in the literature. See, based on this epsilon or c, this RBF varies something like a very sharp peaked or to a flat function. And that improves, I mean, depending on the value of this epsilon you choose, the rate of convergence can be improved, but at the expense of the numerical conditioning. So that means there is a trade-off between the accuracy and the stability in the system. And in fact, this is also valid in the conventional numerical methods. Okay, right. So there is a global radial basis function based schemes. These are highly flexible and exhibit very higher order convergence. But when the size of the data is very large and it produces collocation systems with highly ill conditions. See, once highly ill condition means the stability is coming down. I mean, it's reduced and hence prone to the round of errors. So that means at one time the round of errors will dominate the solution, and then maybe you will get maybe simply junk. So one has to be careful. And the domain decomposition is a good technique for controlling this ill conditioning effect. So that means this uncertainty between the better accuracy to worst conditioning or better conditioning to the bad accuracy, etc., can be up to certain extent can be controlled by using the domain decomposition. But as far as this particular presentation is concerned, we have used so RBF based local Hermite approximation. Again, I will make it this clear in a few slides later, with the PDE centers. Again, this is again I have to show you what exactly is the PDE centers, etc. Okay, right. So basis function of this includes boundary operator, a PDE operator, with two types of data centers, say source centers and PDE centers. So this is what I'll show you. Right. So these two types of centers, say your source centers, PDE centers, can be coincided at certain places. In such case, it's called collocated distribution, or they can be placed independently in the domain, and in such case, we call that as a staggered distribution. And another additional thing you have seen in the title is the upwinding. So this upwinding is another effect which is generally required in the numerical methods, particularly when you have this convection type of effect in the physical process, where generally you also get the nonlinearity in the differential equation. So to handle such process, you also require something called this upwinding, which is also is up to certain extent is inbuilt into in the system, whatever I'll be showing you. Okay, so I was talking about these PDE points, source points, domains, scattered points, etc., all that. So that you can see in this particular picture. You have some arbitrary domain. Okay, I don't require any regular domain like a square, rectangle, sphere, square, etc. It doesn't matter. So any an arbitrary domain omega can be there which has some boundary. You can also clearly mention. And I have two types of points here, source centers, which those circles, dark circles you can see, those are the source centers. I also have something called PDE centers, again distributed in the whole domain, which are represented by dark diamond shaped points. And then you also have certain boundary points, the square dots, where you require to put the boundary conditions into the system. Okay, so this is how, I mean, the points are scattered. I mean, there is no regular connection between the points. You cannot clearly see in this. Right. So how do I make a problem, either interpolation problem or solving a differential equation, whether ODE or PDE? How do I make this problem well defined or well posed? Means there should exist a solution first. It should be unique and also stable. So these are the three properties required. So for that, one can depend on the kind of functions which we are calling as radial functions here. How do we choose those functions so that the developed collocation system is well posed? One obvious choice is positive definite functions. You can see the definition I gave here for the positive definite functions with some coefficients C's here. Okay, how do I characterize this positive? I mean, something similar to what we have is positive definite matrix, very close to that. But here, what we are talking is positive definite functions. So, how do I characterize this? The characterization depends on some Fourier transform. Fourier transform of this, and then a good example of this is the Gaussian function, which you can see here. You can see here that it involves a parameter epsilon here. So based on the value of epsilon, you can give a very flat function to a very sharp function. I mean, either way you can generate such a function. Okay, right. Again, I will not go into the theory due to the short time whatever I have. And there are also other type of functions called completely monotone functions. Again, you can see the definition here. Please note that this bracket L stands for the derivative with respect to the variable, whatever it is. Okay, so this definition gives the complete monotone functions. And again, characterization now, it depends on the Laplace transform instead of the earlier one, Fourier transform. Again, there are certain examples here for this kind of functions. I mean, why I'm giving these characterizations, etc., is how to decide whether such a function is completely monotone or not. On the other side, why I'm looking at these functions is so that my collocation system, whatever I generate using these functions as my basis function in the radial basis functions, are well posed. Okay, that is how these are connected. And this is what is called the inverse multi-quadric, because beta is less than 1. But I am not looking at this particular function as far as today's discussion is concerned. I am taking multi-quadric in which the beta is greater than 0. That's where not the positive definite nor the monotone functions, but there is something called the conditionally positive definite functions. Here again, the positive definite function, the definition satisfies with respect to some condition here, this conditional. So this is the condition required. That's why this is called conditionally positive definite function. And here, this is called a polynomial basis, or indirectly, I have a basis with respect to the radial basis function. And in the definition, I also use or append certain polynomial basis into this and generate these conditionally positive definite functions and use those basis functions in my approximation of the derivative in the solving out differential equations or even in the interpolation problems. Okay, so right. Here, I have one important theorem here for the multi-quadratic functions, particularly for beta is equal to 1 by 2. This is called Hardy's multi-quadratic. For beta is equal to 1 by 2, the condition required is only 1, or we have to add a constant term, that's all. That means 0th degree polynomial precision. Please note that when I say polynomial, it's not polynomial of one variable. Because our dimension of the problem is d. The d can be anything, d greater than 1, right? So depending accordingly, we have to choose. Or for example, if you take thin plate planes, another RBF, here you can see in 2D, you have this x and y, and there are 3 conditions to be satisfied, etc. However, in the...
Sir, are these conditions flexible?
These conditions depend on what kind of RBF you are using and the degree of that RBF. So depending on the degree, one has to choose this basis, the dimension of this basis.
How it will be ensured that the problem can be handled with these conditions, sir?
Okay, because once I have this additional, for example, here you see, if I have this additional basis other than this multi-quadratic, I have additional variable or additional coefficients are there. So here, for example, if I'm solving the interpolation problem, the interpolation conditions ensure that many equations I'll have depending on this n. But these additional unknowns still have to be computed.
Okay.
And for that, I require these additional constraints.
Three parameters are there. That's why you are considering.
That's why I have these additional constraints.
It's okay, sir.
So that in the end, the problem is well posed. I mean, the number of unknowns are what I call is closed system. The number of unknowns and number of equations will become equal.
Okay.
Right? However, for beta is equal to 1 by 2, okay, there is a very interesting theorem which says that once you do the collocation with beta is equal to 1 by 2, even if you don't add this additional polynomial basis, you will see that the corresponding collocation system has exactly 1 negative eigenvalue and n minus 1 positive eigenvalues. That means the 0 eigenvalue is not there, guarantees the non-singularity of the coefficient matrix. That means the well-posedness is, or existence and uniqueness of the solution is guaranteed once beta is equal to 1 by 2. However, in the literature and whatever the work we have done, we have still used this additional constant, whatever I have, because I can have some additional constraint like this, and which gives me a nicely structured coefficient matrix. I mean, I will control my coefficient matrix using this additional condition, though it is not required, right? So, right. So with this theory, that means the existence of a well-posed problem with the radial basis functions under certain conditions, whatever we have seen until now. Right now, let us go to solving those problems of in general, any boundary value problem doesn't matter. But as far as my discussion is concerned, I am more interested in this convection dominant problems. In fact, I can also tell you the reason why I am choosing these convection dominant problems is for such problems, there can be severe oscillations in the solution if you use the conventional methods. The remedies are also known, but the remedies also have certain additional issues, something like our allopathy medicine. I mean, if you have some problem, then we'll take a medicine, but this medicine has certain other complications or side effects. So similarly, there are remedies for the oscillations, but those remedies have again the certain side effects. So those are the things I want to avoid in the computations, right? So that's what we want to highlight here, right? So let us consider any boundary value problem. So this L stands for the boundary, the differential operator, and the B is the boundary operator. I mean, if it is Dirichlet conditions, then B should be just I. But otherwise, there can be, I may have some Newman conditions or Robin boundary conditions, etc. In such cases, B also becomes another differential operator. Okay, and then as we already seen, so any arbitrary domain with scatterly distributed points like this, and also I have highlighted two circles here, which states that since I'm talking about a local scheme here, I'm not worried about the global scheme which I have talked about in the beginning, because that has issues of ill conditioning, which I want to avoid completely. So therefore, and after all, these differentials are the local property. And so why should I bother about the entire domain for the approximation of a derivative at a particular point? So therefore, I choose a local domain for a point, say xk. So this k stands for the local point. Similarly, the j stands for local point here. So as far as this point is concerned, I take some neighborhood and then worry about the approximation of the operator within those points, right? And those points may have source points, and some of them may be PDE points. Again, I have not made it clear, but I'll come to that point a little while later. Or it may also have some boundary points. That means the operator will change whenever there is a boundary point here, right? Now, let me come to the approximation now. See, I want to approximate the unknown function u at the point xk. That's the meaning of this, okay? Which is a combination of quite a few points. What are they? These are the source points. I mean, that's where I take my radial basis function, right? This is something similar to the conventional numerical schemes, whether it is finite difference, finite volume, finite element, all those schemes. This is similar to that. And then we add the boundary points also into the picture here, along with the boundary operator. And not only that, this is where the PDE points comes to the picture. Along with this, I'll add the PDE points. I'll also use the operator on the my radial functions, something similar to Hermite interpolation, if at all you have gone through that. This is similar to that. And then this is my polynomial basis for the well-posedness of the problem. Okay, so this many coefficients are there. This ns number of alphas here, nb number of another additional coefficients here, and npde number of pde points, and then you have the basis, polynomial basis. So depending on the conditionality of the that, I must have these additional points also. So this many points are there, and that is what I am explaining here. Okay, so this psi can be, it's up to you what is the function you are using, satisfying those conditions whatever we said earlier. And as far as this discussion is concerned, that is fixed as the multi-quadric, which is nothing but 1 plus epsilon square r square with m by 2. M should not be an integer, strictly speaking, but as far as this is concerned, I am taking this is not the m, it is the nu actually in the beginning. If you recollect, that nu should not be an integer, but m can be an integer, m by 2 can be an integer, so I am taking 1 by 2 here. Okay, so for that the characterization is completely known. I mean, that gives you a very well posed problem. That's what we know already. Okay, so this gives, if you do the collocation, whatever I was talking about, we can generate a system like this, right? And with A taking the shape like this, with operators whatever we have defined in our approximations, these are the ones you see. And also, fortunately, you can also see that whatever we get here is a symmetric system. That's what. And from this, we can generate what is called a reconstruction vector for the computing the u values here. That's what is required ultimately, right? U is required by computing these alphas, substituting the alphas in the approximation. And once you substitute alphas in the end, I require the u. And this u can be computed using this, and where this h is called the reconstruction vector. And all our operators, whatever we will be using in our problem, okay, so they all appear here. And then finally one can also write there is also a source term on the right hand side. So when I am defining this, there will be a source term depending on the equation. This is where here, this is the source term. So this source term can be computed based on this. Okay, right. So I will not go into the details because of the constraint whatever we have, but ultimately we can generate a linear algebraic system like this by doing these approximations whatever I have talked. And this is the system. Once we come to, we need not worry about whatever the approximations we have done earlier, and how to solve the system, which is exactly similar to any other numerical method, right? any other like conventional methods, where in the end you will end up with some linear systems to be solved. Of course, the size of the system is very, very large, particularly the n value. Okay, and one can use depending on the structure of A, that is how sparse it is or how dense it is. Depending on that, one can use any of the known iterative methods to solve the system. And here, since my the local domain, whatever I have used here, contains only very few points compared to the entire domain. So definitely the quotient matrix, whatever I'm getting here, is a very sparse matrix. Of course, this doesn't have a structure like what you have seen in the conventional finite difference method, where we can clearly give a structure unless there is a particular distribution of the points within your local neighborhood, which anyway we don't want to give as far as these techniques is concerned, right? And once you want to, of course, this is for the steady state problems. Once you go for the time dependent problems, then you do the discretization for the space terms. And as far as the time is concerned, maybe you can give an implicit approximation, something like this. And then you make a boundary value problem, that is the steady state problem like this. And for every time level, you have to solve whatever we have discussed. That's all. So that means you repeatedly use the scheme, whatever you have developed for the steady state, for the unsteady problems. That's how we can also solve the time dependent problems. Okay. Now another, just the last one, this upwind biasing. As I said, to avoid the oscillations. Okay, let me put it physically, this idea. I mean, what exactly this upwind? Assume that I am solving a fluid dynamics problem and the flow is from left to the right. If the flow is from left to the right, why should I use the information on the right? Because that is the future. In my approximations, I should use only the left side information, which is the past. So when I'm trying to understand the present, I should use the information from the past, not from the future, right? Similarly, if the flow is from right to the left, then I should use the information from the right. That is exactly what is the upwind biased, upwind approximation. Mathematically, if you look at it, for the linear systems, whatever we are talking about in the end, AU is equal to some right hand side B. If this quotient matrix is diagonally dominant, then for any initial approximation, okay, any iterative method, those conventional iterative methods, if you use, it is going to converge to the solution of the system. That is a sufficient condition. It's not a necessary condition, but it's a sufficient condition. And once you have that sufficient condition satisfied, then you can, without any hesitation, you can use any iterative method without bothering about what is the initial approximation, and then you can still get the converged solution. Of course, here I'm not talking about how fast and how slow. No, I'm not talking about that. But at least my convergence of my numerical method is guaranteed. And that is where mathematically, if you look at these upwind bias schemes, for particularly these convection diffusion equations, mathematically I can prove that the ultimate numerical approximation, the discretized system, whatever I got, it is diagonally dominant. So therefore, the iterative methods I'll use to solve those algebraic systems are going to converge. That's the advantage I'll get. So this upwinding now, what I'm saying is, for conventional methods, is very easy. If I have points in a line and then I'm approximating at the center point, say I, then upwind means I minus 1, I minus 2, I minus 3 if the flow is from left to the right. Right? So that's easy to identify points. But if the points are scatterly distributed like this, how do I identify these upwind points? Idea is here. Because I am talking about the flow direction, that means I know the velocity direction. Once I know the velocity direction, I'll draw a normal to that velocity direction at that point where I am approximating the derivative. And then all the points which are on the left side of that, the flow direction, opposite to the flow direction, whatever the points are there, those are the points I'll call them as upwind points, right? That's what this figure shows you. So following these ideas, I can also put upwinding in the source terms, or I can also put upwinding in the PDE points, right? So I hope it's clear now what is my source point, what is my PDE point. Source point means I don't use any operator here in the approximation. PDE point means I'll use the operator also along with that. See, this is what. So these are my source points. There is no operator here. These are my PDE points. Okay, this is where the operator comes to the picture here. right? That's what is the difference between those 2 points. So various combinations I can create and look at the solutions with the different, okay. In 1D case, the upwinding, how it is. In 2D case, of course, for the sake of understanding, I am putting a structured distribution of the points. You can see here. And then we'll go to some convection diffusion problems here, and then see how the solutions can be. You can see a second order rate of convergence here for this. And then here you have another problem, convection diffusion equation. Here there is a parameter k here. Based on the parameter, maybe 80, 120, 160, this is what is in the literature is available. The problem here is, as you increase the value of k, you can see that the solution, this is supposed to be the solution. If I increase the value of k, this curve, whatever you're saying, it comes closer and closer to the boundary. Similarly, here also closer and closer to the boundary. So that means what is happening in most of the region, the solution is a smooth solution. However, once it comes to the boundary, close to the boundary, the solution suddenly changes to a very high value. You see here, it's a value of 300 and value of 100, but more or less it's close to 0 as far as this part is concerned. This sudden change is the issue in computing the or use solutions using any conventional methods. This is where you see highly oscillatory solutions. Here, any numerical method will capture the solution accurately, but the accuracy is compromised in these 2 corners. So this is what is called the layered solutions. And this gradient, whatever you see, will drastically change in narrowed regions once you increase the value of k. That is what I mean. On the other hand, you can see here, I mean, of course, the problem for 80 I have solved here. You can see that conventional methods will give a percentage error of 20%. So that means in the solution, 20% is almost error. Okay. But on the other hand, the present one, you can see it's very less. As you increase the value of k, you can see the percentage error also is increasing and completely spoiled. The solution is completely spoiled here. On the other hand, still it is better here. Okay, this is what I'm telling. You see, based on the k value, so the gradients will increase. The change in the solution drastically changes in the boundary corners of the domain. Okay, I'll also show you, of course, I can also a few examples where I have nonlinear problems with coupled equations and things are there. And the solutions are accurate. But more interesting one is maybe the last one here. This is a problem where you have discontinuous boundary conditions. These discontinuous boundary conditions, what they do is create certain kind of oscillations like this in the solution. I mean, this is the best solution which is available in the literature. I mean, I'm showing you these oscillations here. On the other hand, you see that I don't have any such oscillations in my, very nicely the solutions have been captured with whatever the discontinuity which is there in the boundary condition, which is not influencing my solution nicely. Similarly, you have another example here. See the oscillations here, the way the oscillations are there in the existing ones, but my solutions are wisely given. And this can be extended to the problems of fluid dynamics and then Navier-Stokes equations and etc. This is the time dependent problem because I have already reached the time. So I'll stop here. So if you have any questions, maybe I'll be happy to answer. So thank you for your patience.
Oh, sir. Great lecture, sir. Very good.
Thank
sir.
you. Thank you, sir.
Very informative. Sir, any questions from the audience? Hello? Hello. Sir, I have some
Yeah, please, sir.
questions. In the second problem, first example and second example, you have considered the semi-linear.
Reaction also is there. K, because of the K.
For quasi-linear or highly non-linear, how it will be effective, sir?
Okay. You mean the quasi and highly nonlinear means the highest derivative is the nonlinear.
Yeah.
Because I'm more from the fluid dynamics. That means I must have my convection and diffusion processes very clearly. So once I say convection, so I should not have a nonlinearity in the diffusion. I may have my coefficients of the diffusion can be non-continuous because my fluid domain may be of different fluids and then corresponding viscous coefficients can be different and hence there can be discontinuity in those values. So that is that.
You know, I am working on one of my areas is porous medium, and you have just examine the thesis of Kushal.
Ah,
So
yeah.
in porous mediation, nonlinearity comes in the diffusion terms actually. So that's why whether we can apply this method to that kind of problem.
See, strictly speaking, the application of this doesn't stop you
Yes.
using the nonlinearity in the diffusion. I mean, it doesn't come to the picture.
Mhm.
But only thing is, I have not tried any of those examples because my interest is always these incompressible fluids.
Uh-huh.
So we have not tried. But as far as the method is concerned, there is no restriction on
Okay, sir.
using those equations. Yeah.
Those are questions. And sir, you have defined conditionally positive definite.
Yeah. Yeah.
What type of conditions?
Yeah, that's what is the basis. See, those conditions I have shown you, sigma of some lambda coefficients into either the based on the basis of the polynomial which we are adding. For example, I am adding a first degree polynomial in two-dimensional domain. Then the basis is 1, x, and y. So conditions are something like sigma of some add the additional coefficients lambdas, lambda dash, lambda double dash, along with this 1 x, y, etc. And then sigma of that has to be 0. Basically, what I am trying to do is these lambdas are nothing but the coefficients I have used in the usual approximation, and they have to be orthogonal to these additional basis whatever I am giving. Because if I am putting additional basis, the orthogonality is the obvious one is required. I mean, without
Yes,
that, I
yes, sir.
cannot
Yes.
solve the
हाँ,
problem.
वो जो इसमें
So
नेट
that's
नहीं
why I
आ
require
रहा
that orthogonality.
है सीएससी में कौन आता था क्या नाम
Yeah.
है उसको फोन कर विशाल जी को पता है ना
Sir,
तारीफ हाँ, ताजीफ कर
it
दे
is very interesting.
उसको
Very interesting. We'll try, sir.
ताहिद
Thank you.
हमारे पास है नंबर
To crack our problems with your numerical method.
Yeah.
Okay.
I mean, there are other, I mean, which appeared in JCP, Journal of Computational Physics. I mean, that's what
Okay.
we
JCP,
look for
yes.
any fluid dynamics person, particularly the computational methods.
Uh-huh.
That's the best journal. And
Okay.
where we have applied these two, there is one paper in 2008 where we have applied these to the basic fluid dynamics problems. The benchmark problems have been solved. One can see the method there. I mean, because in this presentation, I cannot go into all the details
Yes, sir.
in
Yes,
very
sir.
short time. So one can also look at those papers and can get the details of the method to know the details of how to implement, etc. So those are anyway.
So Professor Som, hello.
Yeah, I think he's
Please.
on a call, I think.
Any other question from the audience? I have already told. Hello, Professor Sahu. Hello.
Hello.
Sir, any question?
No, it's fine. No problem.
We are
because it
fortunate
is
to
already
have
discussed.
Professor Sanyasiraju. He is very busy and he was out of station. But just for our request, yes, I think, sir, you have returned yesterday night, correct?
Yeah.
Yeah, yesterday night.
Yeah,
And
no, actually,
today
what
is
happened was these
presenting.
3 days, there are so many things planned earlier. Yeah,
We are
this
really,
December
we are
end.
really-
December end. So
We are grateful that you have joined
thank you,
here.
sir. Thank you.
Sir, Professor Som, sir.
yes let me thank the speaker as well as the chair for a nice session, nice talk, and really a good deliberation. And now the talk session, invited talk session is over for today's morning. We'll have paper presentation now. So I request Dr. D. Ghosh to chair the session. The paper presentation in the area of what is called optimization. So I request Dr. D. Ghosh to chair.
Professor Sanyasiraju,
Yeah,
you
thank
send me that two remaining papers, sir. I have already.
No, I have not received those two. Can you just send me an email with
Yeah,
the
I
attachment?
have sent it, sir.
Oh, you sent it. Okay,
Yeah.
I'll see.
Okay,
Yeah,
because
thank you.
okay,
Yeah,
we have to submit
today
it in
itself.
the office.
Yeah, I'll finish today itself. Thank you.
Okay.
Thank you, sir. Thank you, everyone.
Sir,
Bye.
thank you.
Namaste.
Hello. हाँ
Mm.